Okay, now let's move to the next slide. Okay, now I will talk about an extension, which is another algorithm. Actually, we can even sit down here and devise an algorithm to solve this problem. It is only going to yield us a solution as long as we don't know how good is the solution or how bad is the solution. It is only going to be an exercise. However, if you can operate 35 people at the same time, and each person can come up with a solution, then if we select a solution among the others, the best solution in this classroom, then probably that solution will be a good solution. It will be better than the average. Now, if I add up the other sections, and if each person solves the problem in his or her own way, then it will be even better, and we're going to have a better solution. So you can see that if you don't know much about the structure of the problem, the one thing that you can do is you can solve the problem repeated in a large number of times and get the solution. Actually, it turns out that that was one of the methods that was used in 1970s. It was called better than most, when computers were not that good. Even for small-scale problems like this or other difficult problems, this was a good way of solving problems. Just solve, let's say, 5,000 times, get a good one, get the best one, and that is reasonably going to be a good one. Of course, we want to insert more knowledge, information on this problem, so we can come up with better algorithms, hopefully. So one of the better algorithms that is already given in your text is the triangle insertion algorithm. Now, this is an algorithm which is used in many different types of problems, not only in the traveling salesman problem, but it is also used in some other problems, and it is very reasonable. Now, let's see what we do with this problem. Now, first of all, the triangle insertion algorithm starts with an already available solution. Now, whereas in the previous ones, if you recall here, we were actually constructing a solution. Okay? Am I right? We were saying that we start at W, we're going to go to P, then we're going to go to C, so on and so forth. We were constructing the solution. Whereas this triangle insertion algorithm is going to work if you have a solution available. Now, the idea is very simple. The idea is based on the improvement idea that we have been talking about. So what it does is, if you already have a solution, so let's have a solution written here. Let's have the worst solution that we found up to this point was W, C, A, P, S, W. So this is a solution that we already have. So this is this step. Now, add a new node. It simply says that you add a new node and all arcs connecting to other nodes. So basically what you do is you simply take a node and add a new node somewhere over here. So you simply shift the location of that and check whether it is suitable to place it here. For example, what you can do is you can take S, put S here, make a computation. Put S here, make a computation. Put S here, make a computation. Take the one which is better than the current one, or the best among all the ones that you tried. This is basically what is meant by the triangle insertion algorithm. Now, the algorithm gives a good solution, probably. At least locally, we are doing a good job. It is not very time-consuming, but of course, we cannot say anything about the optimality. It will be better than the previous one, or at least as bad as the previous one, the same value, but that's it. So let's look at I think in the next page, we have the algorithm itself. So let's apply the algorithm step by step to this example. Okay? And so that we will understand. So choose a pair of directly linked nodes link the new node to each of them. So, for example, let's select S. I have selected S. So what I will do is choose a pair of directly linked nodes. For example, WC is one such pair. So WC is the pair that I selected. And link the new node to each of them, and then eliminate the old link. Calculate the additional cost created, which by this. Now, so what I will do is, now by doing this, I am going to have W, S, C, I'm going to insert it in the middle, AP, W. Now, so what you do is you take it out from here and insert it to here. Okay, so this is actually not a very difficult operation, but this is actually what is meant by the triangle insertion algorithm. Okay, now, of course, this algorithm can be utilized like this, but in general, how do we utilize in practice this kind of a problem? Now, consider the network that you have. So this is one way of applying it. So what you do is you compute everything, the new cost, and if it is better, you accept that solution, otherwise you don't. So this is the logic of that. You basically take something. Now, which one are you going to take? Can you take more than one? Not at the same time, but you do it with different runs. So this is the idea of triangle insertion algorithm. Now, the best place that it is utilized, on the other hand, is as follows. So any questions on the logic in general? So what you do is you take it out from somewhere and put it in another location and recompute. Of course, the recomputation of the cost is not going to be very efficient because you have to compute everything one by one again. Now, how is this algorithm used in general? And let me show that to you. Okay. So this is basically an extension of the same problem, but it's a better use of the triangle insertion algorithm in practice. Now, our original network was something like this. So we have S, C, P, W, A. So this was our original network. Now, next morning that you wake up, you find out that as you are doing a good business, a new city is added to your cities that you need to travel. Okay? So we have city X being added to the network. Okay? Now, previously, the way that I was flying was I was flying from W to C, from C to A, from A to P, from P to S, and from S to W. That's my previous flight. Now I'm going to have this X coming into picture. This is the best way of applying the triangle insertion. It tells the logic, actually, of the algorithm. So what you do is very simple. This X may go here, between W and C. It may go to in between C and A. It may go in between A and P, or it may go in between P and C, or it may go in between S and W. So this new node that you add in can go anywhere. Okay? So what I can do is now I can do those computations. Okay? So I am simply deciding on when to go to X, in between which two cities. Any questions on this? I think it's simple and straightforward. Now let's look at how the computations are done. I think that's the important part. So let's say that I am inserting it in between. We had WC, so we have WA and then AC, and the remaining is going to be the same. So the cost which is added is simply going to be the value of the arc WA and the value of the arc AC minus the value of arc WC. So this is the edit cost when, this should be x. Let me do it as x, I'm sorry. So this is going to be Wx, the new node, plus xc minus Wc. Okay? So this is the edit cost when node x is inserted in between W and C. Now, the remaining part of the network is going to be the same, am I right? So the computation is very efficient. Now, of course, you're going to try and insert x to different arcs, in between different arcs, and then select the best. Now, why not have this kind of an idea to construct the whole path? Okay, well, I will say that, but I think I have to, first of all, ask whether everything is clear. So we can actually do an example here. For example, let's say that I need to create distances. But basically, let's say that the Wx is 15 and xc is 125. And let me also consider the second part, which is from W to C. And so xc and xa is 120. So let me have these three information given to you, and let's apply it to the example. So now, what I am doing is I am going to insert x in between WC. So the cost that I'm going to incur would be 15 plus 125 minus what was the value of WC in the original network? 114. So this is going to cost you 26. Okay? Now, what is the other alternative? Let me go to the second step. I can insert x in between C and A. Okay? So it means that I am going to have CXA. Okay? So I am going to have CX plus XA minus CA as the additional cost. So let's do that for the second one. So this is in between WC, and here it is in between C and A. So what is CX is 125, and XA is 120, minus what is the value of CA? 104. So this is going to be 141. So you can see that if those are the choices that I have, I'm going to select this one and insert x in between W and C. Okay, but we're going to do the other ones. Now, what does this mean? This is basically a simple procedure, but it looks very logical. Isn't it a little bit better than the nearest neighbor idea? Now, well, we don't know. Of course, we cannot say this is always going to yield a good solution, but probably by doing more operations, it is going to be a little bit better than the nearest neighbor. Now, how do we really implement these type of procedures? There are many different ways of doing it. The first one was, if you recall, I can simply say that this is the complete network, and I'm only going to change its location, like we started how to do that. Or what we can do is, let's say that we have n nodes in the problem. I know that I can solve simpler problems, am I right? Because as n increases, that's the case when I'm getting the problems. Why don't I divide, let's say it is a 20-node problem. I divide that problem into 5 problems, and I solve a problem with 6 nodes. Okay, take any 6, solve the problem with 6 nodes. Then what I will do is I will take the 7th node, insert it. Take the 8th node, insert it. Take the 9th node, insert it. And I will do this until all the nodes are inserted. This is going to be probably a good solution. At least the starting point looks very promising. Of course, there are numerous different ways that I can obtain the starting network. But at least this is an improvement, and it might be something that you may want to try. So you can see that actually you can bring in a number of things, create combinations, create algorithms for these type of problems. And believe me, there is no end to that. In other words, you can always do a little bit better by doing this. So it's like a game that you really like to play and want to play. Now, whenever this topic is taught in the classroom, everybody says that, well, why don't we do it this way? It looks that if we do it that way, it will be better. Of course, for this problem, it might be better, but you never know whether it will be better for general. Now, this is basically the difficulty of the problem. So how are we approaching to this problem? We are approaching this problem by solving it with some heuristics. So we have already created a heuristic. Now, let me take your ideas and create another heuristic. So what we have is we have a problem where we have, let's say, n nodes, and we want to solve the TSP. Any ideas that you can bring in will be helpful, because I may reformulate that idea and ask it in the exam. Give you a simple algorithm and ask you to apply it. Okay, any ideas to solve this problem? We have seen 2 of them. One of them is basically nearest neighbor. The other one is a triangle insertion algorithm, which might be applied in various different ways. And of course, the third one is total enumeration, which gives the optimal solution. Okay, but any ideas for a heuristic procedure? Any ideas? Anybody who read, did you read question number 4 or 5 in the homework? Okay, there's another idea, am I right? What it does is it looks at 2 at a time and makes sure that you actually, well, how does it do? I don't remember actually. I mean, but that's a heuristic. So anything that you can suggest actually. You can start with a solution, or you can construct a solution. Okay? Anything? Any ideas? No ideas? Okay. Well, let's look at the problem. Maybe it will give you an indication. Let's look at this specific problem. And what is the best possible solution that you can have? How many arcs are you going to have in a solution? Let's start with that. 5 arcs. Okay. Now, what will be the best solution that you can obtain with 5 arcs? Look at the problem and tell me what that can be. Now, we don't know whether it will be possible or not, but the best possible solution would be what? Yes?
I would say VP.
Okay, don't say VP, but generalize it.
No,
Okay. Now, looking at the numbers, you can say something. But what will be a solution that you will say, oh, definitely this is the optimal solution? If it was feasible, of course. Yes?
Summation of the smallest numbers in the arcs.
Okay. Some smallest 5 numbers that you see in the arcs. Okay. So let's do that. Okay. Sum of smallest 5 arcs. Okay, tell me what those are. The smallest is 65. The next smallest is 74. The next smallest is 76, and then 98. and then 104. Now let's look at the corresponding arcs. This is CS, and 74 is PW. 76 is AW. 98 is CP, and 104 is CA. Okay. Now, do you think that this is going to give us a feasible route? How did you figure that out? There is an S here, but there should be two. Okay, now and what is a property then? A property of the problem, if there is an entering, there should be at most two arcs entering and leaving a certain node. If you don't have that, it's not a feasible solution. Okay, so we have a few words that we should learn. Number one, feasible solution. Feasible solution means that we have a Hamiltonian path. Okay? If it is not a Hamiltonian path, it's not a feasible solution. Okay? So Hamiltonian path, it should be a Hamiltonian, and unfortunately this doesn't form the Hamiltonian path. However, it gives us valuable information. Let's add all these up. What is that value? 202, 270, 282, 350, and no, I think it should be something with 400s. Why don't you add somebody who is quick in adding up? 470. 17. Okay. Okay. So this is the best solution that you can obtain. Now, if it was a Hamiltonian path, we would have no doubt that this would be the best solution. So now we're getting some information out of the structure. Can we use it when we are constructing a solution? Can we use this information when we are constructing a solution? Yes. These are very valuable arcs, and we want these arcs, at least some of them, to be in the solution. So one heuristic would be start with these arcs and only correct it when you see that it's not feasible, and then go ahead with that. For example, you already have noticed that S is missing here. We should have, there are 3 C's and 1 S. So the first thing that we should do is we have to find another arc from C or to C, doesn't matter, which is going to replace one of those arcs. Maybe then we're going to get a feasible solution. But to do it that way, the best thing is to take the graph and simply show on that graph the arcs that we have selected here. Now you can bring it to a complete Hamiltonian path by changing only one of them maybe, or 2 of them. You can do that. So that's actually an approach that you can take. Now, another important information is 470. I know that this problem is going to have at least a cost of 470. Now, what if I have a solution which is 422? What can you say about that solution? It's very good. Okay? If it's a solution, it's very good. So we started to have benchmarks, actually. Now, what you're going to learn in 202, 303, even if you have a very difficult problem in question, you would learn how to construct these type of bounds. Okay? So this is called, actually, a lower bound to the problem. A lower bound is a value which you are sure that your objective function, your performance measure value, will never be lower than that value. Okay? So it is called a lower bound. So you put a lower bound on the value that you can attain with a Hamiltonian path. Now, what was the original solution that we had? 462. So now what we have is, we have 462 is a solution that we have with the nearest neighbor, if you remember. And then here we have 417, which is the lower bound. Okay? Now you can say that if I accept this solution as the solution to apply, what is the most improvement that I can do is sort of if I can move from here to here somewhere. And it gives you an understanding of the improvement that you can do in this problem. Okay. So there are many ways of looking at it, but I think the idea is that when you start looking at a singular problem, you obtain more information. Now, let me pose the question again. Any other ideas for a heuristic? Any other ideas or suggestions for the solution of this problem? You see, the more you look at the problem, the more you will learn about the problem structure. Yes?
I found a path lower than 460.
Okay, so, okay, well, we can have that path. How did you find that path?
It's kind of by chance, but...
Okay, you actually enumerated. You enumerated all possibilities. Okay, that's how you obtain that, which is valuable, but again, I may increase the number of nodes, so you wouldn't be able to generalize that. Okay, so it is valuable. We will appreciate when you give us the number. What's the value? 457. Okay. Is this the best solution? For those of you who had checked the course notes? Okay, good. But the idea here is that we don't want to confine ourselves to solving a single instance of these problems. We want to make sure that we have a good approach, a generalizable approach, which is going to solve all similar problems. That's the aim. We're not solving puzzles. Okay, you solve a puzzle and then you're set. But what we are solving is we are learning how to solve many puzzles of the same kind. So we have to have an approach to solve that. That's the reason why these type of observations are very valuable, but you have to be systematically approaching the problem. Otherwise, every time that you obtain a solution like this, I can increase the number of nodes by 1 and ask you again, and maybe you will be able to answer that. Then I will increase the number of nodes by another 1, and there will be a limit after which you won't be able to find any solutions. Well, the best solution. It will become more difficult. Okay, any suggestions for heuristic procedures? You don't want to give clue to me with respect to the exam. Am I right? Okay, any suggestions? Last time? Okay, if you don't, I think this is where we end the class. Any questions? Okay, thank you.